Hi, my name is Zachary Lyons, and today I'll be presenting the Lab 4 Oscillations Lab for Physics 2211 at Georgia Tech. In this lab, the goals are to compare the predicted motion using a computational model with the observed motion from a tracker analysis of a mass attached to a spring. The energy of the system was then plotted to show the changes that occur in the system for the predicted motion. The energies in question in this lab would be the change in kinetic energy, gravitational potential energy, spring potential energy, and the total energy of the system, or the change in energy of the system. It was found that the predicted motion and the observed motion are very similar in both the x and y axes, but there was more similarity in the x-axis. The change in the total energy of the system is 0 in this lab. This lab focuses heavily on Newton's second law, which states that the net force acting on an object is equivalent to the change in the object's momentum over the change in time. This relates heavily to the velocity update formula shown below, as well as the position update formula, which were used in the computational model for this lab. The energy principle states that the change in energy of a system is equivalent to the work done by the surroundings, as well as plus the exchange of thermal energy between the system and the surroundings, as shown here. The energy in this system would be the kinetic energy of the mass, the spring potential energy, as well as the gravitational potential energy. These equations are represented in the computational model as well. The system in this lab would be the Earth, the spring, and the mass, with the surroundings being nothing. This means that there is no work done by the surroundings and no transfer of thermal energy between the system and the surroundings. This means that the change in the energy for the system during this lab is 0. That means that the change in energy of the system is equivalent to the kinetic energy of the object, the gravitational potential energy, as well as the spring potential energy. The tracker analysis is shown here with the X and Y data being stored in the graph below, as well as the table. The table was then transferred to an Excel file, which was then transferred to a CSV file so that it could be represented in the computational model. The video's frame rate was 10.53 frames per second with a seconds per frame of 0.095 seconds. The object's mass was given at 0.402 kilograms, and it was observed that the start time was 0.475 seconds, and the initial position and velocity is shown here with the initial velocity being 0. The time of the last observation was 9.877 seconds. These initial conditions are then represented in the computational model with the link to the computational model shown below. These are the constants for this lab, where the acceleration due to gravity is equivalent to 9.8 meters per second squared, and the spring constant can be derived using the equation below using the period of oscillation, but it was provided that the spring constant was 6.83 newtons per meter. The relaxed length of the spring was 0.123 meters. The equations were then represented in a computational model. As seen here in lines 92 to 96, the energies are represented by the equations from the previous slides, and the change in those energies are shown over here. The velocity and position update formula is related here, and the force due to gravity and the force due to the spring are represented in these lines. The net force is then the sum of the spring and the gravitational forces. This is a video of the model. I could speed it up for time. But as you can see here, the computational model represents the motion of the object, and it tracks its motion as it moves. The graphs are then shown. In this graph with the changes in energy, it is seen that the change in energy is constant at 0 as the object moves, and that the X and Y data are very, very similar, but the Y position data is not as accurate based on the computational model. The change in energy versus time graph shows that the change in energy of the change in gravitational potential energy and the change in spring potential energy are opposite signs, and they oscillate back and forth. The kinetic energy also oscillates and switches signs with the gravitational potential energy as it moves, and is in a lesser magnitude than the other energies. The X position versus time graph shows that the computational model is accurate. The Y position versus time graph shows that the computational model is not as accurate at predicting the Y motion relative to the X position. There are potential sources of error, however. The model does not account for other forces like drag. The model doesn't account for other energies like rotational kinetic energy, and thermal energy with the surroundings. The center of mass may also not have been consistently tracked when being put into the tracker analysis. So, is the energy principle satisfied? Yes. Using the change in energy graph, the sum of the change of kinetic energy and the change in gravitational potential energy and the sum of the spring potential energy is still seen to be 0, which equals the total energy in the system, which is also 0. So the principle is upheld. Thank you.